A photonic integrated circuit or integrated optical circuit is a device that integrates multiple photonic functions and as such is similar to an electronic integrated circuit. The major difference between the two is that a photonic integrated circuit provides functionality for information signals imposed on optical wavelengths typically in the visible spectrum or near-infrared 850 nanometers-1650 nanometers. The most commercially utilized material platform for photonic integrated circuits is indium phosphide, which allows for the integration of various optically active and passive functions on the same chip. Initial examples of photonic integrated circuits were simple two-section distributed Bragg reflector lasers, consisting of two independently controlled device sections, a gain section and a dBr mirror section. Consequently, all modern monolithic tunable lasers, widely tunable lasers, externally modulated lasers and transmitters, integrated receivers, etc. are examples of photonic integrated circuits. Current state-of-the-art devices integrate hundreds of functions onto single chip. Pioneering work in this arena was performed at Bell Laboratories. Most notable academic centers of excellence of photonic integrated circuits in NP are the University of California at Santa Barbara, USA, and the Eindhoven University of Technology in the Netherlands. Recently, a large amount of funding has been invested into developing photonic integrated circuits in silicon. A 2005 development showed that silicon can, even though it is an indirect band-gap material, still be used to generate laser light via the Raman nonlinearity. Such lasers are not electrically driven but optically driven and therefore still necessitate a further optical pump laser source. Comparison to electronic integration: unlike electronic integration where silicon is the dominant material, system photonic integrated circuits have been fabricated from a variety of material systems, including electro-optic crystals such as lithium niobate, silica on silicon, silicon on insulator, various polymers and semiconductor materials which are used to make semiconductor lasers such as GaAs and InP. The different material systems are used because they each provide different advantages and limitations depending on the function to be integrated. For instance, silica-based PICs have very desirable properties for passive photonic circuits such as AWGs due to their comparatively low losses and low thermal sensitivity. GaAs or InP-based PICs allow the direct integration of light sources and silicon PICs enable co-integration of the photonics with transistor-based electronics. The fabrication techniques are similar to those used in electronic integrated circuits in which photolithography is used to pattern wafers for etching and material deposition. Unlike electronics where the primary device is the transistor, there is no single dominant device. The range of devices required on a chip includes low-loss interconnect waveguides, power splitters, optical amplifiers, optical modulators, filters, lasers and detectors. These devices require a variety of different materials and fabrication techniques, making it difficult to realize all of them on a single chip. Newer techniques using resonant photonic interferometry is making way for UV LEDs to be used for optical computing requirements with much cheaper costs, leading the way to PHZ consumer electronics. Examples of photonic integrated circuits: the primary application for photonic integrated circuits is in the area of fiber optic communication, though applications in other fields such as biomedical and photonic computing are also possible. The arrayed waveguide grating, which are commonly used as optica multiplexers in wavelength division multiplexed fiber optic communication systems, are an example of a photonic integrated circuit which has replaced previous multiplexing schemes which utilized multiple discrete filter elements. Since separating optical modes is a need for quantum computing, this technology may be helpful to miniaturize quantum computers. Another example of a photonic integrated chip in wide use today in fiber optic communication systems is the externally modulated laser, which combines a distributed feedback laser diode with an electro-absorption modulator on a single InP-based chip. Advantages of photonic circuits: photonic integrated circuits can allow optical systems to be made more compact and higher performance than with discrete optical components. They also offer the possibility of integration with electronic circuits to provide increased functionality. One challenge to achieving this level of integration is the size discrepancy between electronic and photonic components. The emerging field of nanoplasmonics is focused on creating ultra-compact components for realizing truly nanoscale photonic devices to match their electronic counterparts. An example of the new breed of components is a recently proposed novel type of bandpass plasmonic filter that uses a response similar to electromagnetically induced transparency to achieve multi-channel filtering. This allows easy control over the filtering wavelengths and bandwidths for applications in wavelength multiplexing systems for optical computing and communications in highly integrated all-optical circuits. Photonic integrated circuits should also be immune to the hazards of functionality losses associated with electromagnetic pulse, though may not be immune to high neutron flux. Current status: photonic integration is currently an active topic in U.S. defense contracts. Silicon-based photonic analog signal processing engines with reconfigurability, federal business opportunities. FBO.gov. Retrieved December 21, 2013. Centers in Integrated Photonics Engineering Research, Federal Business Opportunities. FBO.gov. Retrieved December 21, 2013. It is included by the Optical Internetworking Forum for inclusion in 100 GHz optical networking standards, contracts, CEI 28G, paving the way for 100 gigabit. Infinera Corporation develops and vertically integrates 100 GB per second and 500 GB per second photonic integrated circuits in commercially available long-haul optical transport networking platforms. Infinera's 500 GB per second PIC was named Best Optical Component Beyond 100G at the 2013 Next Generation Optical Awards. See also, Nanophotonics, Optical Computing. References. Notes. References: Larry Coldren, Scott Corzin, Milan Mashinovich. Diode Lasers and Photonic Integrated Circuits. John Wiley & Sons. Macaulay, Alistair D. Optical Computer Architectures, the Application of Optical Concepts to Next-Generation Computers. Goa, A. Ramnarayan, R. Stein, M. Proceedings of the 14th Annual International Symposium on Computer Architecture, ISCA 87-145 doi, 10.1145/30350.30367. ISBN 0818607769. Ultra Corporation. Overcome copper limits with optical interfaces. Brenner, K.H. Huang, ALll. Logic and Architectures for Digital Optical Computers. J-Opt. SOC. AM. A3, 62. Bibcode, 1986 OSAJ, 3. 62B. Brenner, K.H. A programmable optical processor based on symbolic substitution. APPL. OP27, 1687 Euro 1691. Bibcode, 1988 AP Op 27.1687B doi, 10.1364/AO. 27.001687. PMID 20531637.